Chi Zhang. Dr. Chi Zhang completed his doctor program at the TUM, Germany. And now he's worked as a postdoctor in TUM, and his research interest is in the development of open source multi-physics and multi-resolution libraries based on the SPH method, and also its application in fluid dynamics, solid mechanics. And he has published more than 30 journal and international conference papers. And today he will give a presentation with the title "An efficient fully Lagrangian solver for modeling wave interaction with oscillating wave energy converter." Okay, Dr. Zhang, please.
Okay, I will share my screen.
Okay. Okay, you can share
Okay.
the screen.
Okay, can I see it?
Yes, I can see, no problem.
Okay. Okay, thanks, Professor Liu, for the kind of introduction. And first of all, I want to thank Professor Wan and all the local committees for organizing this fantastic workshop in this hard time. Also, thanks for all the speakers for their great presentation. Okay, having several presentations, I think we'll have a lot of talk about CFD, and also most of them based on mesh-based method. So let's have something different, fully Lagrangian method. So today my presentation will be talk about an efficient fully Lagrangian solver for modeling wave interaction with the oscillating wave surge converter. And this presentation includes the work in our team led by Professor Xiangyu Hu, also cooperating work with Dr. Wei from ACDIS Hydraulic, also Professor Diaz from UCD. So this is the outline of this presentation. First of all, I will talk about the background and the motivations. Then I will give the brief summary concerning the numerical principles and the validations of our open source library, SPHinXsys. Then I will give an introduction to our new developed CAD-compatible body-fit particle generator. And after that, I will give the coupling procedure of SPHinXsys with SymBody, multi-body dynamics library. And then the main course of today's presentation and the modeling of wave interaction with oscillating wave surge converter will be given. And after that, the concluding remarks will be present. So as we know that wave energy converter have received more and more attention in recent years because wave can travel long distance with little energy loss. Another important feature of wave energy converter is that the wave offers the highest energy density. Also, the wave energy converter shows limited negative environmental impact. In this figure, we have shown several types of the wave energy converter. For example, this is the observer wave point observer wave energy converter, and this is the topic we'll talk about today, the oscillating wave surge converter, and this is the type. And also another important is the oscillating wave column here, as you can see here, and this map shows the percentage of different wave energy convert in 2016 reported by the ERC Ocean Energy Status. So as we know that experimental study is time-consuming and economic expensive in the study of the wave energy converter. Therefore, numerical study has received more and more attention due to its time efficiency and economic benefits. And in the past decades, and there was many two approaches for the modeling of wave energy converter. One is the linear potential flow, which is based mainly on BEM, and this approach is efficient and fast. However, this approach can only simulate the nonlinear hydrodynamic effects of the fluid when the fluid is interacting with the structure. Also, only small amplitude of the structure can be modeled. And here we list several solvers based on the linear potential flow. Also, in recent years, CFD solve approach, where the Navier-Stokes equation is solved, has received more and more attention due to the development of computer source. And the main feature of the CFD solver is that the nonlinear hydrodynamics can be studied. Also, varying the motions of the structure can be investigated. However, compared with the linear potential flow, the CFD-based approaches is computationally expensive. And also, the CFD-based approaches can be divided into two parts. First is the mesh-based solvers. Another one is the mesh-free solvers. Fluent and open form is widely used for the simulation of wave energy converge, and also SPH and MPS nowadays have received more and more attention for the development of the numerical solvers for modeling of the wave energy converge. So next, I will talk about what is the SPHinXsys. So first of all, I will talk about why we want to use the SPH method, as we know that the SPH method is a fully Lagrangian method. Therefore, as an extreme stable genius have said, trust the Lagrangian. So SPH method has shown his a lot of advantages after his first inception since 1977 for the astrophysics applications. And in SPH method, the material is represented by a set of particles, and each particle carry mass, moment, and several other hydrodynamic property, for example, pressure, temperature, and internal energy. In SPH method, function derivative and integrals are approximated by the interactions of neighboring particles with the type of the kernel function. Here is an example of a kernel function. This is a basic shape, and the kernel function will determine the neighboring particles and also the interaction between each neighboring particles. So the SPH method has several advantages. For example, SPH method can easily handle the complex physics because the material in each system can be divided by their own size of particles. Also, treatment of larger deformation is much easier compared with the mesh-based method. Also, identify free surface flow and moving interface and deformable boundaries is an easier task. Also, modeling fragments, for example, splashing with breaching and brittle fractures is seamless for SPH method. So, SPHinXsys is a open source meshless multi-physics and multi-resolution library developed in our group since 2 years ago. And the open source meaning that SPHinXsys is under the Apache license version 2.0, and it can be used for commercial implementation. Also, the meshless meaning that we are using the unified SPH method for modeling fluid, solid fluid structure and other problems. Also, the multi-physics meaning that this library is aimed for industrial complex system. For example, multi-phase flow, fluid structure interaction, reaction diffusion, and also the reaction diffusions coupling with the solid mechanics. And also the multi-resolution meaning that the library applies a multi-resolution and multi-time stepping algorithm. And in this link, you can find us in the GitHub, or also you can find us the library in the YouTube channel. For the fluid dynamics, the SPHinXsys solves the Navier-Stokes equation, and using the SPH method, we can discretize this equation in this form. And then if we introduce the interparticle average velocity and pressure, so we can rewrite this equation in this form. We note that in this equation, the momentum is conservative. So again, as extreme genius have said that conservation ruins the supreme. Also, to close this system, we need an artificial equation of state. Here we use the linear equation of state, and in the weakly compressible assumption, the fluid is assumed that its density is varying less than 1%. Therefore, the Mach number is about 0.1. Then the speed of sound can be said as the 10 times the maximum speed of the fluid. So in the previous work, we have said that we can introduce inter-average particle velocity and pressure for the discretization of the momentum and the continuum equation. So if we introduce a Riemann problem between each interacting particle, for example, particle I and particle G, then we can use the solution of the Riemann problem to replace the interparticle average velocity and pressure. Then we can rewrite the equation like this. By introducing a Riemann solver, we don't need to use artificial viscosity for the momentum equation. Also, if we assume that the star region of the left and the right state is constant, then we can get to the linear Riemann solver here. But this solver is show excessive numerical dissipation. It applied directly to the simulation of violent flow. Therefore, we introduce a low dissipation limiter to control the numerical dissipation. Here, with the limiter, there is no dissipation is introduced under the action of an expansion also. And this small number meaning that the dissipation will be modulated if the action of the compression wave is occurred. Then we have to talk about the treatment of the solid boundary. So why this is important? Because think about this joke. So what's the question of a particle as its neighbors? So it may, I think it should be, where is the boundary? So in the Riemann-based SPH method, we're using the dummy particles for the solid. For example, we use the dummy particles to represent the solid wall, and this is the fluid particles. Then we can calculate the normal of the wall in this equation. And after that, we can construct a one-sided Riemann solver between the fluid particles and the solid particles, not along this direction, but along the normal direction, point from solid particles to the fluid particles. For the one-sided Riemann problem, we have the left state based on the property of the fluid particles. Then we can construct the right state based on the velocity of the solid particles and the equation of the state. Then we have the one-sided Riemann problem. And also, this boundary treatment have show optimized the computing efficiency because there's no interpolation is required for the wall particles. So it's a benchmark test. It's widely used in SPH community, and it's also has been talked in Professor Hu Changhong's presentation in the previous presentation. And here we can see here, using the SPH method, you will have a very small number of fluid particles and all the property of the Dunbridge flow, for example, a very high run up, then a very large second jet. And after that, there was a very violent free surface breaking and re-entry. All these feature is well captured. Also, this is the comparison between the simulation of the experimental. And after that, we compare the elevation of the free surface and also the pressure signals. This is the comparison of the elevation of the free surface. As you can see here, SPH method can accurately predict the variant free surface elevation. Also, this is the pressure signals. You can see here, even the variant free surface is accurately predicted. However, a very smooth pressure signal is reproduced, and this pressure peak is well captured. So then we extend the Riemann SPH method to the multi-phase simulations. If we have to introduce another scheme, for example, if we use the summation equation for the light phase and using the continuum equation for the heavy phase, then the heavy flow will be treated as a free surface flow, and the light phase flow will be treated as an internal flow. Then we can rewrite the linear Riemann solver into a multi-phase Riemann solver property. Also, we have to include the low dissipation limit. Here, there were two main features of the platinum multi-phase solver. One is that the same speed of sound is applied both to the light and heavy phase, which will achieve optimize the computing efficiency. And then there is no void region around the solid particles. So this is the test for the solution. This is experimental, and this is the simulation results. There will be maybe some voice in the experimental. As you can see here, the simulation captured the violent free surface breaking and impact. Meanwhile, there is no separation of fluid particles and the air particles. Also, we compare the signals of the pressure sensors. As you can see here, we also compare the results of the multi-phase to the single phase. We can see both simulation results have a good agreement with the experimental data. However, compared with the single phase simulation, the multi-phase show less magnitude of the pressure peaks due to the existence of the air particles. And then we will talk about the SPH solver for the solid dynamics. For the simulation of the solid dynamics, we implement the total Lagrange SPH formulation, which meaning that we can define a deformation map from the initial reference configuration to the deformed configuration, meaning the current configuration. Then we can define the deformation tensor as this, and then we can have the first parallel stress and the second parallel stress. And having these two stress, we can have the mass and the linear momentum conservation of this equation. And then by introducing a kernel correction, we can have the SPH discretization of this governing equation in this form. Again, we have an inter-average particle parallel stress, which means that the momentum conservation is ensured. Then we validate our solver for the cantilever bending. This is the setup of the cantilever bending. This end is fixed, and then the cantilever can be deformed freely in the body by imposing an initial velocity. Here we set an observer at this point. This is the video of the deformation of the bending. We have applied two nonlinear material models, New-Hawken and the Horsford-Ogden. Here we compare the present results of the time history of the point S with the FEM simulation results. As you can see here, for both material models, the deformation of the cantilever is accurately predicted compared with the FEM solver. Then we validate the solver in another benchmark test, the oscillating beam. This path is fixed, and the beam will moving freely by imposing an initial velocity in this direction. And this is the deformation of the free end by using different resolutions. And as you can see here, as the increase of the resolution, the convergence results is reached. Also, we compare the present results with the analytical one by imposing 3 different initial velocities again. And for these 4 cases, a good agreement is noted. And then we validated the solver in another famous benchmark test, the twisting cantilever. This test is very challenging for both FEM and the SPH method due to its very large deformation during the twisting. And this is the initial setup. And as you can see here, in the present solver, the larger deformation is well predicted by the present total Lagrange SPH method. And then we coupled both the fluid dynamic solver and the solid mechanics solver for the simulation of the FSI applications. For the fluid model, we use the Riemann-based SVG method, and here this represents the force, the pressure force exerting on the solid, exerting on the fluid by the solid. This is a viscous force exerting on the fluid by the solid. In the solid model, we have another 2 forces. These forces have different directions. So in present FSI coupling, the surrounding solid particles is behaving as a moving boundary for the fluid. And then we apply the no-slip boundary conditions in the fluid structure interface. So by applying a multi-resolution FSI solver, we use different smoothing lengths for the fluid and the solid subdomains. Generally, for the computing efficiency, the smooth length of the fluid is larger than the smooth length of the solid. So then we can rewrite the fluid coupling force in this form. As you can see here, for the solid particles, we're introducing an imaginary pressure and velocity. Here, the imaginary pressure and velocity is interpolated from the fluid particles. Also, we have introduced the average time average of the velocity and the time average acceleration for the solid particles. This is because that we are using a multi-time stepping method, which means that if the fluid particles have one-time integration and the solid particles have several time steps of integration. Therefore, if we use the current velocity and the acceleration of the solid particles, there will be force mismatching in the fluid structure interface. Therefore, we introduce the time average velocity and acceleration for the accurate computation of the fluid structure interaction. So this is a benchmark test for FSI solver. Here, this is a hydrostatic water, and we have elastic structure at the bottom, and the two end is fixed. Then, under the interaction with the hydrostatic fluid, the structure will be deformed. Here, we recorded the time history of the middle point of the structure. In this figure, we have shown the constant structure resolution, meaning meanwhile varying the resolution of the fluid. As you can see here, this is the analytical solution. As the increase of the fluid resolution, the simulation results will converge into the analytical one. In this simulation, we have keep the fluid resolution as a constant, then varying the resolution of the structure. Again, a good agreement is noted. And this is another case which is widely used in the immersive boundary method, the flow-induced vibration. This is the setup. Here we have an inflow, and here we have an outflow, and then the up and down is the solid wall boundary conditions. And here we have a cycle fixed, and then an elastic beam is attached to this cycle. So when the structure is interacting with the surrounding flow, the vibration will be generated. This is the simulation results, and this is the results of the deformation of the beam. So this is the time history of the position of the free end of the beam. As you can see here, after 50 times, a stable oscillation is reached. And then we have conducted a convergence study by varying the resolution of the structure and also the fluid. As you can see here, as the increase of the resolution, a convergence is reached. Also, we compare our results with the data in literature, and both of these three data is using IBM method. So we can see here, the present SPH-based FSI solver can accurately predict the structure, the deformation of the structure. So we also implementing GPU acceleration in our library. And here we have that test of the solution in 3D. And this is the CPU information we are using. And this is the GPU information we are using. And for these particles, another one is about 1.5 million particles. As we can see in this figure, as the increase of the number of particles, the total speed up can be reached about 53. So this work is our ongoing work, and right now we only have the GPU acceleration for the fluid simulation, and in the future work we will do the both FSI solver with the GPU acceleration. So right now we have talked about the numerical principles and the validation of the SPHinXsys. Then before we go into the model of the wave energy structure, we have talked about another important topic, the particle generator. So as we know that SPHinXsys do not need a mesh. However, we have to set up the initial distribution of the particle. So generally, there was two methods for the particle generator. One is the lattice. So we directly initiate a particle on a lattice structure, as you can see here. And this method can generate asymptotic and equalized particle distribution, and it's easy to implement it. It's widely used in the particle-based method. However, this method cannot generate a body-fitted particle distribution. As you can see here, there is no body-fitted for the cycle. Also, portraying the correct surface for complex structure is very expensive and very hard, especially in 3D geometry. Another particle generator is using the volume element mesh. And in this method, particles are generated at the center of a mesh element. Then the particle volume is said to equal the element volume. And this method is widely used in the pre-processing tools of commercial software. And this method can accurately portray the complex surface. However, this method has the non-uniform particle spacing and volume, and this will reduce the numerical accuracy. So therefore, we have introduced a CAD-compatible body-fitted particle generator. The CAD meaning that this particle generator is started by passing a CAD file. For example, you can create any geometry by using a CAD software and output it in a STL or OBJ file. Then our code can read this file automatically. And after passing the CAD geometry, we will build a level set function based on the background mesh, like this level set field. And then we will initiate particles in the lattice structure if the level set function is inside the geometry surface, as you can see here. And then we will have several time steps of relaxation, and also with the surface constraint, then a body-fitted particle generator can be generated. So the physical relaxation is governed by this equation. Here we have the pressure force and the viscous force, and also we also have the surface constraint. The surface constraint meaning that, so for example, this is the surface of the geometry, and this we move this surface about the distance of half of the particle spacing. Then if one particle is moving out of the geometry, it will be moved back exactly at this line. So in this case, a body-fitted particle distribution can be generated. So there were several examples by using our CAD-compatible body-fitted particle generator, and all these examples have very complex geometry. As you can see here, this is a propeller, and it has a very sharp surface. Also, this is a hard model derived by using the image. And this is the particle distribution for two standard structures. So in present particle generator, all you need to do is generate a CAD file, and then our library can reach the CAD file automatically, and then give to the relaxation with the particles constraint, and then give you the body-fitted particle generator. So having talked about the particle generator, we will talk about the coupling with the SPHinXsys with multi-body dynamic solvers. So for the multi-body dynamics, we are using the SymBody. SymBody is an open source multi-body physics library. It's widely used in the simulation of biomechanics. This is an example by simulation of a mine running with the SymBody. As you can see here, it can deal with very complex multi-body dynamics. And in this example, a lot of body is included. Also, they will contact and interact with each other. So as the SymBody provides a C++ API, then it can be coupling with SPHinXsys straightforwardly. This is the basic overview of the coupling between SPHinXsys with the SymBody. Here, if the SymBody gives some impulse, and the SymBody will use it as a parameter for solving the governing equation, then it will have some results. And then the SPHinXsys can use these results to update its new state. So this is the detailed coupling procedure between the SPHinXsys and the SymBody. In the present coupling procedure, the fluid structure coupling is conducted by SPHinXsys, and then the total force and the torque exerted on the solid is computed, and then the total force and torque is sent to same body, and the same body will solve the Newton and Euler equation. After that, it will do the time integration, and then the new kinematic states will be sent back to the physics, and the physics will use the new kinematic state for update particle position and velocity for the solid particles. This is the detailed algorithm for the coupling. So as we know that SPHinXsys method can solve the Euler-Newton equation directly. However, if we're using the coupling of a multi-body library, we can deal with a very complex example. This is the one example. Here, we have a channel flow, and we will have a dead fish, and this fish will constrain to a fixed point through a cable, and this fish have two parts. The head part is a solid part; it cannot be deformed. However, the other part is flexible. This means that when the inflow is interacting with the dead fish, the fish body will be deformed, and then it can extract the energy from the flow, and then it will be swimming forward. And this is the experimental results conducted by Bill it was published in GFM, as you can see here. When the fish body is extracting energy from the flow, it can be swimming forward. Here, we reproduce these results by using the present physics solver. Here, this is the fish, and this is a half cylinder, and then the fish body can extract the energy from the flow and then swimming forward. So we have shown that the present solver can accurately do the simulation of the fluid structure interaction, and it also can do the simulation of multi-body dynamics by coupling with the same body. Then we will do the simulation of the wave interaction with oscillating convert. So this is the main concept of the oscillating wave energy converter. It have two parts. This is the oscillator. It will be put in the water, in the sea, and this is the basin. So when the oscillator is interacting with the wave, it will change the mechanical energy to a high-speed flow through the high-pressure cable, and then the station will use the high-speed flow for generating electric. So this is the full-scale model, and this is the model in the operation when it is put in the sea. So this is our numerical setup. We follow the experiment conducted in the Belfast University. And this is a setup. We simplified the oscillator into a flap type, and we have 3 wave problem here. And this is a 3D file generated for the numerical setup. And using the previous particle generator, you can generate the particle distribution for this numerical example automatically. Then we'll have the piston type wave maker, and we also have a wave elimination in this damping zone. And for the validation, we will start the wave h equal to 5 meters and the wave period equals to 10 seconds. So this is the movie of the simulation and also the experimental. As you can see here, when the wave is interacting with the flap, a very large rotation motion is produced in the simulation, and the present solver can accurately capture the motion of the flap. Meanwhile, the pressure field actually is very smooth, and this is the results of the experimental. As you can see here, there was a very clear slamming phenomenon is observed in the experimental. However, in the simulation, there is no visible slamming phenomenon is generated. We believe that this may be due to the fact that the resolution is not high enough. So maybe in the future work, we can study this slamming phenomena for increasing the resolution. So this is the validation for wave elevation and the flap rotation. This is the procedure for 3 wave problems. We compare the numerical results with the experimental data. As you can see here, For the wave problem number 4, which is far away from the flap, a very good agreement is noted. Well, for the wave problem number 5 and number 12, there was some small discrepancy, which is due to the fact that when the fluid is interacted with the flap, there is obvious leaking occur. Therefore, there's some difference between the numerical results and the experimental data. Also, we compare the time history of the rotation motion of the flap. We also compare our results with the data in previous SPHinXsys results. Here, as you can see here, compared with the previous SPHinXsys data, the parent solver actually show improved accuracy. And also the present results have a good agreement with experimental data. Also, we show the total force exerted on the flap. As you can see here, the force in the x direction actually is the main force induced the motion of the flap. And then we compare the wave floating on the flap with that. The wave loading actually have a key role in the design of the wave energy structure. In the experimental, we have 13 pressure sensors, and we choose 6 of them for the comparison. For the pressure sensor number 1 and pressure sensor number 3 and pressure sensor number 11, and these 3 pressure sensors is close to the free surface. Therefore, as you can see here, for the SPHinXsys results, a very visible pressure peak is observed, and the magnitude of the pressure peak is larger than the observation of the experimental. This is due to the fact that the SPHinXsys method applied a weakly compressible model, which will increase the pressure peak of the fluid. And for the other 3 pressure sensors, as you can see here, a very good agreement is noted. So then we can go to the computational efficiency. And we know that SPHinXsys method is generally considered to be computational expensive compared with the mesh-based method. And in our library, we have several algorithm for the improvement of the computational efficiency. For example, using the multi-resolution and also using multi-time stepping. Here is a comparison of the time efficiency with Fluent and other 3 SPHinXsys solver. And this is the computation time for physical, for example, several time of physical times. And this is the number of the corresponding cells or particles. And this is the information of the device. For comparison, we normalize the computing time by the physical time and also by the number of the particles or cells. As we can see here, for 1 second physical simulation with 1 million particles, the Fluent required about 60 hours of CPU time. And also, this is the result of a UCD SPHinXsys code. It required almost 120 hours. However, using our solvers, it only required 3.6 CPU hours. And compared with the dual physics, which have the acceleration of the GPU, and right now we do not using the GPU acceleration. The parent solver can also show improve the computing efficiency. As you can see here, for the physical simulation of 13 seconds, and it only requires 8.5 hours. It means that, so you are working on your code whole day, and then after 1 day work, you send your simulation task to your machine, and then go home, and next morning you can check your results. This is very important for a very large number of particle simulations. We think that in the future work with the GPU acceleration and this computing efficiency can be improved improved, which means that if you send your simulation task to your desk machine, then you can, after maybe a coffee break, you can check the results. After the validation, we also start the power takeoff system by using a linear damper. Introducing a linear damper to the angular velocity, we can rewrite the Gaussian equation in this way. Here, the KD represents the damper coefficient. Then we can compute the capture factor by using the power taken by the structure, and then this is the energy of the wave. So here we show the time history of the rotation of the flap for several damper coefficients. As you can see here, as the increase of the damper coefficient, the rotation is decreased. However, this figure also shows that if we increase the damper coefficient, the decrease of the rotation is not linearly decreased, which means that the power takeoff in the real condition may be a nonlinear phenomenon or a nonlinear process. Also, we have shown the time history of the pressure signals for the 6 pressure sensors. And also, one interesting thing is for these 3 pressure signals, you can see here, as the increase of the damper coefficient, actually the peak pressure is decreased or eliminated, which means that if we apply the power takeoff system in the wave energy convert, when it puts in the real condition, actually the pressure loading may be not as large as we observed in the experimental or in the simulation results. This figure shows the variation of the capture factor when we increasing the damper coefficient. As you can see here, it first increased, then decreased. So the optimized capture factor is reached when the damper coefficient is equal to 40. So then we also start the extreme wave loading on the flap, as we know that predicting of extreme loss on the device of wave energy converter or even on the wave structure is important for the design of the structure. Also, experimental study for the extreme loss is time and economic expensive. Therefore, we can use the present numerical solvers for the simulation of this condition. Here, we use the focused wave approach, and we set up the focused position close to the flap position, and then we set the focus time equal to 50 seconds. And this is the elevation of the free surface, as you can see here. About at the time of 50, an extreme wave is observed, and this is the time history of the rotation of the flap. Again, when the extreme wave is interacted with the structure, a very large rotation is produced. Here, we show the time history of the pressure for the 6 pressure sensors when the extreme wave is interacting with the flap. Again, as you can see here, as extreme wave is interacting with the flap, a very large peak pressure is noted. So then we can go to the concluding remarks. So we have developed an open source mesh-less multi-physics and multi-resolution library based on SPHinXsys method. And we have validated this library for fluid dynamics, solid mechanics, and fluid structure interactions, and also multi-phase flow. And for the particle generation, we have developed a CAD compatible body-fitted particle generator, which can reach a CD file, and then a body-fitted particle generation will be conducted automatically. And then we have developed an efficient solver for the mode of the wave interaction with the structure by coupling with SPHinXsys with symbolic, and then we validated the solver by simulation wave interaction with oscillating wave surge convert, and also the power takeoff system and the extreme wave loss are also investigated. So you can find the information about the library on GitHub. Also, contributors are always welcome. And if you want to join the development of library, please contact with us. Okay, thank you. That's all.
Okay, Dr. Zhang, thank you very much for the presentation. You have presented very high-level research works for the particle method. And
okay, thank you.
It seems it's very promising method, not only for the fluid dynamic problem, but also for the structure problems. It's very impressive. Yeah. Thank you. And now it's open for discussion. Any questions or comments for Dr. Zhang's presentation?
Any comments or questions?
Okay, now I have a question about the body-fitted particles you have mentioned in your presentation. It looks interesting. So is that means it is possible to do some kind of, for example, to model the boundary layers for example, for the Han Renan number problems? Is it possible for the SPH method?
Yeah, now looks like it's possible because we have accurate representation of the complex structure. And I think that if we want to do the LES simulation for the high Reynolds number flow, and maybe we need the multi-resolution of SPH method, which meaning that we also have to increase the particle resolution when the flow is near the boundary. So that is also our ongoing work. We have developed a multi-resolution SPH method. Actually, in previous work, it's based on discrete the fluid domain and solid domain by using different resolutions. And in our ongoing work, we are working on developing adaptive particle distribution, which means that the particles will adapt its resolutions in the computer domain. So in this way, I think we can do the simulation of the LES SPH modeling for complex structures, maybe in the future. Yeah, that's the case.
Okay, thank you very much for the explanation. And are there any more questions?
Yes, thanks, Zhang Ci. Very excellent work. Yes, yeah, you present many good works. So I just one question. You said you combined SPH with the same body, right? Oh,
yeah, same body.
So this means the same body is the what's the difference with the fluid structure interaction? So this is a special kind of package of the same body. Yeah.
Yeah.
Could you give the more the explanation?
Okay. Same body actually is a multi-body dynamics library. It deals with the multi-body physics problem. For example, in this video, actually you can see it includes a lot of solid bodies. And we have bones and even the muscles. So it deals with the multi-body dynamics. So if we're coupling SPH method with the same body, it means that we can deal with fluid interaction with multi-body dynamics, not even a single body. For example, in this case, actually this case is a multi-body problem, and we have a cable which is connected to the fish, and also this fish have two paths. One is the solid path, another is the elastic path. If we're using just SPH method, actually we can simulate, for example, this problem, and it's simple. It's simple to easier because this path is fixed. We don't need to move the whole body freely in the flow. However, when coupling with the same body, we can deal with more complex problem of the multi-body dynamics. So, for example, if we can define a cable which is connected to a fixed point to the fish body. Also, maybe in the future work, for example, we can let the same body do the simulation of a man which can be swimming in the water, and then we will just coupling the physics with the same body. The same physics will calculate the fluid dynamics and then compute the force interacting with the solid body, and then we send all this force to same body, and the same body will control the solid dynamics. For example, it will receive the total force and the total torque from SPHinXsys, and then update the state of the multi-body dynamics, and then send back the new state, and the same SPHinXsys can update the new position of the solid particles. So in this way, we can do the simulation of the fluid interaction with the multi-body problem. That's just what we want to do.
Mm-hmm. Okay, good, thanks.
Thank you.
Mm-hmm.
So, any other question?
Mm-hmm.
I have a small question.
Mm-hmm.
In the twisting example, in the twisting case, you said, so I have a question that how do you twist the object?
Actually, this is, as you can see, this is a cantilever, and this end is fixed. And if we give the cantilever twisting initial velocity, for example, a different angular velocity along this direction, and then with the initial velocity, the cantilever can be formed in the twisting way. That's what we do. We just initiate the body with different angular velocity.
Oh, so velocity.
It's like this. For example, in this case, the velocity is in this direction, right? And in the 3D case, actually, we can impose angular velocity along the cantilever in this direction. Actually, in the X and Z phase, we can impose angular velocity.
So you impose angular velocity to all the particles in the object.
Yeah, that's the case. So then the particles will, for example, for the out particles, the velocity will be the angular velocity is the same in this phase, and it will increase along this direction. Okay. Generally, this is the initial setup.
Okay, I understand. Another one is the sloshing or dampering case. In that case, how does the fluid particles interact with the solid walls? I mean, how do you define the velocities around the wall and the forces around the wall?
So there was a lot of difference between the experimental and the simulation. As you can see here, in the experimental, actually the tank is moving. However, in the experimental, we do not let the wall move. We just give how to say, the gravity in this direction to the fluid. Then the tank can be simulated, the simulation phenomena. So there is no moving of the wall in the simulation. Also, you can do the simulation of the wall. It's also easier, but I think in this case, it's much easier. You just give acceleration to the fluid in this direction. It's fine.
Oh, so you give a gravity forces on the.
Yeah, in this case, we have two gravity. This is the normal gravity, and then this is the gravity for the sloshing motion.
Oh, okay, I understand. Okay, thank you.
Okay, thank you. Okay, if there's no more question, we can stop here.
Okay, if there are no more questions, and let me invite Professor Wan to give the closing speech for the fourth CMHL symposium. Okay, Professor Wan.
Okay, so now it's come to end of the symposium. Yeah, so anyway, yeah, I think that today